So we start. So in today's lecture, we are going to look at nomenclature based on hydrocarbons, which are cyclic. And last time we looked at the saturated ones. So in other words, like you guys looked at lipids, we said they are saturated and unsaturated. In the same way with organic compounds, we have aliphatic and aromatic. Then on the aliphatic, we said we have open chains. We also have the cyclic. These are the ones that we are going to look at. Now, in the class of the aliphatic and the cyclic chains, we have the alkenes, the same hydrocarbons that are linear, that is alkenes that are sp3 hybridisation, alkenes sp2 hybridisation, alkyls sp hybridisation are the same with the aliphatic hydrocarbons in cycles. So last time we looked at open cycle chains, that is with hybridization at sp3, that is alkenes. Now today we are going to look at nomenclature with hybridization at sp2, which are double liaison. Now we are saying for you to name any cyclic chain, we are supposed to first consider the chain principle. And the chain principle, like we stated last time, was the cycle itself. The cycle itself is Lassen Principle. So it contains the highest number of carbon atoms. Then whatever is substituted to the chain principle, which is the cycle, becomes a substituent. We've been looking at this for a while. So now the question is, how do we name cyclic hydrocarbons that contain or have a double liaison? So how do we do it? We do it in this way. So like we're naming alkenes, that is the ones that have the hydrocarbons that have a double liaison. We are always going to start from where the double liaison is. So the double liaison in our case will give us the direction of how the methyl or the substituents are going to be aligned. So example number one. Now, how do you count it? You always give the double liaison the smallest index possible. The smallest index possible. So that is rule number two. So we count it from here, say position 1, position 2, position 3, and not position 1, position 2, position. So the idea is we are giving these substituents the lowest number possible. Now, if we're to start counting from here and say 1, 2, 3, 4, 5, this methyl here is going to have a position of number 5. Then when you count it from this direction, that is 1, 2, 3, it's going to have a 3. And the idea is we are always supposed to give these substituents the lowest number possible, the lowest number as possible. So we are saying we can either count it from here, here, and there, or we can start from here, go like that. So let me just show that. We can come like this, or go like that. Now, there is a astuce here. There's an astuce that we're supposed to take note. Now we are saying, if you count in this direction, say 1, 2, 3, you are going to have the lowest indices possible. You're going to have the lowest indices possible. Now, if you're to count, we are saying we're supposed to count from the liaison, the double liaison. Now, if you're to count from position here, this one here, in this direction, this alkyl group will have an index of 5. Now, when you compare 3 to 5, you find that 3 is less than 5, and therefore it will imply that we have not respected the rule that states that whenever we are arranging our substituents, we are supposed to arrange them as the smallest indices for these substituents. So in other words, when we are counting, we are going to consider the double liaison to be our start point. Then the other alkyl or substituent will be our endpoint. So in this case, the direction we're going to take will be 1, 2, 3, and not 1, 2, 3, 4, 5. Is it clear for this one? Is it clear for this one?
Yes.
And therefore, the name would be, that is for the chain principle, we say this is a 1, 2, 3, 4, 5. It's a 5-chained hydrocarbon, and the prefix is a penta. Then the terminaison, because we have a double liaison, the terminaison changes to in, that is ENE. So this shows us that we have a pentene, which is an aliphatic hydrocarbon that has a double liaison. Why? Because of the presence of this terminaison, the suffix ENE. Then because it's a cycle, we add cyclo. Because it's a cycle, we add cyclo. Therefore, it will be called cyclopentene. Cyclopentene. Now we come to the substituents and their positions. So we are saying because the substituent at methyl is at position number 3, we are going to now have the name 3-methyl-cyclopentene. 3-methyl-cyclopentene. Is it clear for this example?
I have a question.
Yeah.
Yeah. On the double bond.
Yeah.
The double bond. This one, which is 1, in which is between 1 and 2. When it comes to cycle hydrocarbons, we are not supposed to state we're not supposed to state where the double bond is.
No, as in you can either state where the double bond nomenclature where you position. Okay, the rule is I just forgot to mention this. The rule is when you have a cyclo hydrocarbon or any other chain, we're going to look at this when we do alcohols. You can either position the double liaison at position number 1, or you can leave it when it is at position number 1. When it is at position number 1, but when it is at position number 2, it changes everything. You're supposed to name it. You're supposed to put a 2 there. Say 2-ENE. But when it's at position number 1, you know what 1 does? 1 is like one of those numbers where we consider to like not even put it at all because we know that there is a 1. That's the same principle we are applying here. But when it's at position number 2, we are supposed to make sure we position the the double liaison. The position of the liaison is supposed to be noted in the name. Now, because here it is at position number 1, we can either put it or we can either neglect it. C'est la même chose, ça reste la même. Is it clear? So if you've noticed, even these names here, they remain the same. Why? Because they are all at position number 1. But if there was another liaison, if there was another double liaison, you would have noted the first one and the second one, and you would have used the multiplication factors. So the reason why we are not adding a position for the double liaison in this case, you can either add it or you can leave it just like this. Why? Because when a double liaison is at position number 1 in organic chemistry, we either assume to say the coefficient is 1 that you're going to denote here and say 1, or we're just going to leave it like that because we just know that, okay, it's at position number 1. It's a straight chain. That's how it's supposed to be. Yeah, is it clear for this part? For the first one, cyclopentene, 3-methyl cyclopentene. Okay. Then
I have a question.
You're
saying that we have to give it the list number in the list indices.
Yeah.
But then why didn't you start where there's 2, right? Where you put the 2 there? Why didn't you put the 1 there, counting it from as the double bond where it is? Then where the 3 is, that's where the 2 is.
Very good question. So the idea is when you're counting the double liaison, we are supposed to count both carbon atoms that are involved in the double liaison. Very nice question, Vitaly. You're supposed to take note of the 2 carbon atoms that are engaged in the double liaison, because the carbon at position number 2 and the carbon at position number 1, they are both involved in sp2 hybridization. It's not only this carbon atom. Both carbon atoms are involved in hybridization à l'état sp2. So it is for this case that we are supposed to take them into consideration when we are giving them the indices. We are supposed to take into consideration the indices for both carbon atoms here. because this carbon atom and this carbon atom are different from this one. They are different. They are different. This one, where is this? This one here, this one here, this one here, and this one here. These carbon atoms here are different from this. That is the one at position 1 and the one at position 2. Okay, why do I mean different? They are different in the sense that their hybridization is different, and the bonds that are also formed here. This is SP the SP dehybridization. That is, you have got a pi and a sigma bond. But for these ones here, you only have sigma bonds. You only have simple sigma bonds, and their bond angles. This is 109.5, and this is 120. So this is what differentiates these two from these ones here. This is what differentiates these ones from these ones. So when you're counting, please, you are going to give the index to both the carbon atoms that are involved in the bond. That is the SP de hybridization liaison, which is pi and sigma. You are always going to count both. You are always going to count both. I know some of you might have gone like Mutali stated, to say, why didn't we start from here then go like that? No, we are always supposed to give the liaison. In other words, the liaison is supposed to be given the what's this? The index that is the lowest. Even here in the what's this? The phrase, the sentence, it states that pour nommer un hydrocarbure monocyclique comportant une double ou bien triple liaison, on numérote les cycles de quelque sorte que l'indice de position de la liaison multiple soit le plus bas. The index of the double liaison, triple liaison, supposed to be as low as possible. So if you were going to start from here, 1, 2, 3, 4, 5, you're going to have position number 1 and 5. Then if you start from here, 1, 2, you're going to have 1 and 2. Therefore, the one that you start counting from here will have the highest indices as compared to the one that you start counting from here to this position. So like I said, you are always supposed to take into consideration the double liaison. You are always supposed to take into consideration the double liaison. That is at position number 1 and at position number 2. Then you continue. Is it clear? Is it clear?
Yes, it is.
No questions? Okay, so example number 2. So the same principle, Lassen Principle will be the cycle. The chain principle will be the cycle. That's rule number 1. Rule number 2 is, because we have a double liaison, we are supposed to take into consideration that the double liaison will come first, then the substituent will come later. The substituent will come later. Now, in this case, now how are we going to count? Now, how are we going to count? So we can count in this direction. That is 1, 2, 3, 4, 5, 6. Or we can count, that is 1, 2, 3, 4. Tefio. Isn't it? Yeah. Now, if you remember very well, the rules that we used last time, the rules that is for the ones that do not have a double liaison, we said the substituent, the position of the substituent at some point can also be the beginning of can give us a direction in which we are supposed to count. If you guys got me clearly last time, we said the substituent can also give us the direction. That is alphabetical order if you take into consideration the alphabet and all those things. But I said the substituent can also help you in determining where you are supposed to start from. You guys are supposed to answer, isn't it?
Yes, it is.
So now in this case, we are going to start, other than starting from here, we are going to start from where the substituent is. So we are going to, because rule number 2 states that we are supposed to first consider the double liaison. After considering the double liaison, we come to the substituent. Now here, it will be that the substituent and the double liaison will come in at the same time. They will come in at the same time. So the double liaison will starts from, you can either start from this side or this side. We can start from here and here, for as long as we are taking into consideration the two carbon atoms that are sp de hybridization. Now you have a substituent at this carbon atom. You have a substituent at this carbon atom, and therefore instead of you counting from here to this position, you are going to start from where the substituent is and where the double liaison is also starting from. So in other words, I'm saying rule number 2, which states that you are supposed to come with the double liaison first, then later with the substituent. That's rule number 2. Now, in this case, we are saying because at position number 1, you have the position of the double liaison and you also have the position of the substituent. So when you are giving the indices to this hydrocarbon, the direction you're going to take will not be 1, 2, will not be here 1, 2, but will be 1, 2. Why? Because if we start from here and say 1, 2, if we to start from here and say 1, 2, forget about this substituent, the one at position number 6. I just want to give out an example, like why this thing is coming about in this way. If we don't have this substituent here, if we only had this one here, if you start counting from 1 and say 2, this hydrocarbon here, this is a hydrocarbon as well, we are calling it a substituent, isopropyl. It will have an index of 2. It will have an index of 2. Then if you were counting it from here, this is position number 1 and go to position number 2, it's going to have an index of 1. Now when you compare the two indices, that is 1 and 2, which one is the lowest? It's definitely the 1, isn't it? It's definitely the 1. So in other words, taking this route, that is position number 1, position number 2, position number 3, you are going to have the highest indices possible. You're going to have the highest indices possible. Even if we include this substituent at position number 6 and say 1, 2, 3, 4, 5, 6, we are still going to have the highest indices possible. Now, why? Because we counted number 1 here and we counted number 2 here. Automatically, 2 is greater than, this is 3. This is going to be 1 and 6. Automatically, the 2 is higher than the 1. And therefore, this 2 will not satisfy what we are stating here. Say, la indice la plus bas possible. La indice la plus bas possible. So, what you are supposed to do in a case where you have a double liaison and the double liaison at a position is attached to a substituent, this is what you are supposed to do. Where the substituent is attached to double liaison, like in this case, this is where your lowest index is supposed to start from. This is where your lowest index is supposed to start from. Now, in our case, it will start from position here where the substituent is, and you are going to go like that. You are going to go like that. You are going to go like that. Now, the contradiction that I'm trying to bring out here is, if you are going to start from position number 1 here and say position number 2, in the case where we don't have this one, in the case where we do not have this, you are going to have the substituent, that is isopropyl, at position number 4. Number 2, sorry, number 2. It will be at position number 2. And therefore, when you compare the two, the two nomenclatures, you have one that has you're going to have, let's say the first one we are going to say at position 2 and the second one at position 1. That is for the substituent. Forget about this. I just want to make like an explanation just based on this so that it makes sense. If you're going to start counting from here, say here 1 and 2 like that, the substituent here will be at position number 2. If you count from here and say 1 to 2, it will be at position number 2. But now the rule is we are always supposed to give the substituent the lowest index possible, the lowest index possible. Now the lowest index possible will be that we are going to take into consideration the position of this substituent and the position of the double liaison. That is position number 1. And therefore, 1 is lower than 2. And our direction will be 1, then 2. So therefore, when you're naming this hydrocarbon without this position number 6, it will be isopropyl cyclohexane. Isopropyl cyclohexane. Now, when you add in this methyl, there will be 2 prepositions as well. There will be one that is going to be 1, 2, 3 at position number 3. And the other one will be 1, 2, 3, 4, 5, 6 at position number 6. Now we are saying, because the first indices will just, if you've noticed in all these nomenclatures we've been doing, the first index is what has been giving us the guide on which one we are going to take. Now you find out that the first index here is greater than this one. The first index, which is 2, is greater than the 1 here. At least if we had a 1 here and a 1, we would have said, okay, we are going to take this one, because when you compare the 3 and the 6, 3 is greater, or is less than 6. So therefore, it will be position 3. Then we are going to go to, it will be position 3 and not position 6. But now, the indices are definitely different. Now, we are going to look at the first index and compare it to the second index here. So the first one here and the first one here, the 2 is greater than the 1. And we are stating that the rule is we are supposed to have l'indice soit le plus bas possible. Soit le plus bas possible. Now the plus bas possible here is 1 and not 2. And therefore, this numérotation is going to be outruled, because we are going to have the highest index in this numbering. We're going to have the highest index, that is 2 and 3. And therefore, when we count, we are not going to count in this direction. That is, we're not going to count in this direction, but we are going to count in this direction. That's the direction we're going to take. So that is, the chain principal has 6 carbon atoms. La chaîne principale has 6 carbon atoms. La chaîne principale has 6 carbon atoms, and it has a double liaison. So a 6-chained hydrocarbon is called a hexa. Now we talk about the vowel and all those things. So the terminaison is ENE for any hydrocarbon with a double liaison. That's ENE. Then it's a cycle. Because it's a cycle, we call it a cyclo. And the chain principal will be called a cyclohexene. A cyclohexene, because it's a cycle and it contains 6 hydrogen, 6 carbon atoms. And the terminaison will be ENE to justify that it has a double liaison quelque part. So the same idea. We do not show the position of the double liaison, or if you want, you can actually show the position of the double liaison. That is at position number 1. At position number 1. So our numeration will be 1, 2, 3, 4, 5, 6. So at position number 1, you have a substituent, and at position number 6, you also have another substituent. So isopropyl is this substituent you are seeing here. Isopropyl is this substituent you are seeing here. So it also has another name. Now, this is how you name it. But is it clear so far with numeration and the giving of the indices? Is it clear?
Yes.
Okay. So this is how you name isopropyl. You can name it. You can write isopropyl. It's also correct, or you can name it in this way. So we are going to count. We are going to count the number of. We are going to take this like a normal chain. We're going to take it like it's a normal chain. So we're going to say at position number 1, you're going to go like that. Say 1, 2, tape 1, 2. Then now our longest chain will be a three carbon chain. Like there'll be one here, there'll be another one there, and there'll be another one there, one there, another one there, and another one there. So we said when we're naming hydrocarbons, we are supposed to consider the longest chain possible. That is the longest chain possible. And the longest chain in our case is this thing here. The longest chain is this thing. Now, this whole thing has a substituent. This is the substituent. It has a substituent. And the substituent is at position number 2. When you count it from this side, say 1, 2, or this side, it's 1, 2, c'est la même chose, ça reste la même. It will be still at position number 2. So at position number 2, you have a substituent. Now, what do you call a 3-chained hydrocarbon? What do you call a 3-chained hydrocarbon? It's called propane. That is for sp3 hybridization. It's called propane. Propane. It's called propane. It's called propane. Now, because it's a substituent, because in this case it's not acting as a chain, but acting as a substituent, it will not be called propane, but be called propyl. It will be called propyl. Now, at position number 2, we have a methyl. So it will be 2-methyl. So therefore, the name of this thing, isopropyl, can also be called 2-methyl propyl. Isopropyl can be called 2-methyl propyl. So other than writing isopropyl, you can say 1,2-methyl propyl. The methyl propyl. So other than writing isopropyl, you are going to say 1,2-methyl propyl. 1 that is in brackets, isopropyl, also known as 2-methyl propyl. So let me just re-explain on how we came up with the nomenclature of this substituent. So we are saying isopropyl, if I draw it properly, the one is facing upward. If I draw it like this, it would be something like this. So we are saying the way we do our nomenclature, we say we are always supposed to name the chain principal, or maybe numéroter la chaîne principale. Now, la chaîne principale will be this one here with 3 carbon atoms. That is 1, at 2, and at position number 3. That is our chain principal. And we said a hydrocarbon or an alkane with hydrogen, with 3 carbon atoms is called propane. It's called propane. Now, because it's not a chain, like a normal chain, peut-être, ça peut être ouvert ou bien ramifié. In this case, it's not that kind of a chain. Why? Because it is now acting as a substituent. We are not going to call it propane. We are going to call it propyl because it's a substituent. So it's going to be called propyl. That's the chain principle. Propyl. Then we are saying at position number 1, 2, we have a methyl there. You have a methyl there. Now, at position 2, you have a methyl. You have a methyl there. You have a methyl there. At position number 2, you have a methyl there. Position number 2, you have a methyl. Propyl. You have a methyl propyl. So when you're naming this, when you're naming now this hydrocarbon, bien, this hydrocarbon, c'est la même chose. We are going to say 1 in brackets 2 methyl propyl you close your bracket, you continue 6 methyl cyclohexene. Now, someone will ask me this question, say, Daliso, you have methyl there. Now, which one comes first? So, the one that's supposed to come first is going to be this one, because you're going to have a methyl and methyl there. Now, because you have a P that comes after M, then position number 6 should come first. Then you have this substituent at the end. That is in the case where you want to name it using this type of radical, that is 2-methyl propyl. The nomenclature will be 6-methyl. The correct answer will be 6-methyl. Then in your brackets, that is 2-methyl propyl cyclohexene. But if you use the non-usual, that is isopropyl, it will be 1 isopropyl 6-methyl cyclohexene. Is it clear? Is it clear?
What's the question?
Mm-hmm.
Yeah, so I don't know if I missed something.
Yeah.
But if you consider the chain of it and all that, we said when counting the carbons on the branch, like we don't start from the carbon that is in the main chain. So like I'm failing to understand how we've got a propyl here. The 3 carbons, like
3 carbons. No.
I
don't. This is our chain principle, isn't it? Isn't it? Okay, let me do this. Let me draw it in this way. We have this here as our isopropyl. Which one is going to be our chain principle? You can take it from anywhere. You can take it from this, from like that. It can be a chain principle as well. You can also take it like that. This will still be a chain principle, or you can also take it like that. This will be a chain principle. But what you're supposed to note is that the chain principle in our case contains 3 carbon atoms. It contains 3 carbon atoms. That is 1 here, 2 here, and the last one can be there. Number 1, number 2, and number 3. That's 1, 2, 3. Now in this case, our isopropyl is in this orientation. This is where it's bonded to this cyclo thingy. It's bonded to this cyclo thingy like that. So when we are counting, we're going to count 1, 2, 3. That is for our chain principle. Just this part, the chain principle. Now, What do you call this type of substituent? What do you call this type of substituent? It's a methyl. It's a methyl. So it is bonded at carbon number 1. At carbon number 2, sorry. At carbon number 2, you have a substituent there. That you have a substituent that is going to the carbon number 1. That is the reason why, if you've noticed with the nomenclature of this hydrocarbon, when you do the naming, it becomes 1. Let me just write it. It becomes 1, 2, methyl propyl, like that. So we just end here. Now it shows us that at position number 1 you have this substituent. At position number 1 we have this substituent TEF. Then this whole thing here, if we're to just name it, if we just to name it, just like naming it, like if it's a question, you say, okay, Mr. Kennedy, name this compound for us. If they tell you to name this compound, for just naming it, you will say, okay, Lassen Principle in our case would be at 1, 2, 3. We have 1, 2, 3. That is our Lassen Principle. That is going to be our Lassen Principle. So if this is our Lassen Principle, we are going to say we are supposed to give the index, the lowest index possible to our substituent. Now, our substituent will be the methyl we are seeing here. Now, the methyl has an index of 2. This is where the methyl comes in. The methyl comes in. Now, we are saying, if you're to just name this compound, like this is a compound you've been asked in an exam, say, name this compound. The nomenclature for this one will be called 2. It will be called 2-methyl propane. It will be 2-methyl propane. If you are given this in your nomenclature exam, wherever, so this will be called 2-methyl propane. Now, if it is now a substituent, it's the same thing. It's a 2-methyl propane. Now it now becomes a substituent. Now you get a 2-methyl propane and attach it to this carbon atom here. It still maintains the name of 2-methyl propane, but now because it is a substituent, it will no longer be called 2-methyl propane, but be called propyl, because it has no longer become a chain independent on its own. Now it has become a substituent. So at position number 1, the same things that we usually do. Is at position number 1, you have a substituent, and our substituent in our case is called 2-methyl propyl. Like the same things we were doing at position number 1. You have a ethyl, you have a propyl, you have all those things. It's the same thing we are doing here. It's not only the methyl, the propyl, the hexyl, there are a lot of them. You have, when you do isomers, you understand that some of these chains form isomers. There are some that form tertiary type of bonding. For example, you can have, let me just show you from this table here. Yeah, this is a table here to just show you that you can have a lot of these substituents. It's the same thing, but they are just isomers. So, see, so these are the types of isomers that you can have. You can have amethyl ethyl, that can also be called propane. In a case where this is an isomer, like something like this, you can also have isobutyl, that is 2-methyl propyl, can also be called isobutane. You can have butyl ou bien N-butyl, butyl, can also be called butane. It depends on where the substituent comes in. You can have sec-butyl or S-butyl, which can also be called amethyl propyl, also known as butane. Then you can have the tertiary one I was talking about, that is tiobutyl or T-butyl, that is 1,1 dimethyl ethyl. That can also be called 2-methyl propane, sorry, then tesiobutane. So it's an example of such kind of substituent. It's an example of such kind of substituent. So you can either use the norm usual, or you can name it from here. You can just name it from here. You can name it from here using the nomenclature usual. That is, you count the chain principal. When you finish counting the chain principal, you look at where it is linked to. Then at the end of the day, look at where it is bonded to, like I said. Then you use the nomenclature of the substituent. When I mean substituent, it implies that you no longer have the propane, that is the suffix with either ane, ene, and yne. That is for alkane, alkene, and alkyl. It's different. It's supposed to be in function of the substituent, or the alkyl, alkyl, and alkene group, depending on which substituent you have been given. So Mr. Kennedy, in our case, our chain principal for this hydrocarbon is going to be this one here with 3 carbon atoms. That is 1, 2, 3. Now at position number 2, you have a methyl that is protruding. You have a methyl that is coming out like that. Now at this same methyl, you have this whole thing here. This whole thing is attached to a carbon atom at position number 1. It is attached to carbon number 1. Like I said, like I always say, you are not supposed to count this carbon atom twice. This carbon atom is just once one, then it is attached to this carbon atom. But this whole thing here is a methyl. This whole thing is a methyl. This whole thing is a methyl. It is a methyl. Yeah. So is it clear?
Yeah, it is. Thanks.
Yeah. So is it clear for everyone? So you can either use the isopropyl nomenclature, that is the nomenclature UCL, or you can use the UPAC nomenclature, where you independently name this chain here. You name this chain independently. Then that will be at position number 1, you have isopropyl, and at position number 6, you have a methyl. Therefore, the name will be called isopropyl, this whole thing here, and position number 6, that is a methyl, 6-methyl cyclohexene. And we choose to give the position that is for the double liaison, or we choose not to give it the position that is when it is at position number 1. When it is at position number 1, but when it's at position number 2, we are supposed to make sure that it is given the position. Is it clear? Is it clear?
Yes.
Okay. So I'm saying I'm not just saying Mr. Kennedy, but for everyone. Is it clear for everyone?
Yes, it is.
Okay. So
Yes.
we forge ahead. So the last example on the cyclic hydrocarbons that are insaturated. When we state to say a hydrocarbon is insaturated, it's the same in English. We call it unsaturated. C'est la même chose. A saturated one is the one that has got sp3 hybridization, that's the carbon atoms. Unsaturated one is the one that contains sp2 hybridization, that is the carbon atoms that are engaged in a double liaison or bien a triple liaison, but most of the times it's a double liaison. So in this case, this is the last example for the insaturated hydrocarbons on the cycles. Then the same thing we are going to consider now, that is la chaîne principale, ça va être la chaîne de la cycle. So the cycle here is going to have the principle, the chain principal will be the cycle. The chain principal will be the cycle.
1 o'clock.
Then our numération, it will start from the double liaison. It's the same explanation as this one here. Other than starting from position number 1 here to position number 2, we are going to start from here 1, where the substituent is bonded to the double liaison, or the carbon that is having the double liaison and the substituent. We are going to start from there because we said we are supposed to have the lowest indices possible. That is for the two carbon atoms that are involved in the double liaison. And we are also supposed to take into consideration that the substituent that we have also has the lowest index possible. Now, the only direction that can satisfy this condition is this direction here. Just a minute. Is this direction, like that. When we take this direction, it's only this direction that is going to satisfy these conditions that we are stating here. So if it is a 6-chained hydrocarbon, it will be called hexane. It will be called hexane. Now, because we have the double liaison, the suffix will be ene. That would be now a 6-chained hydrocarbon called a hexa, and a terminazo of ene. And don't forget, every time you are doing this type of nomenclature, there are going to always be the voyelle and all those things. So please don't forget to make that a liaison where you cancel out the a and you remain with a suffix ene. Please take note. Then we're saying it's a cycle. It's a cycle. So for all cycles, and another attention, for all cycles, always put a cyclo. For all cycles, always put a cyclo, except for benzene. Except for benzene, you don't say cyclobenzene, unless in a case where benzene is bonded to a cycle. Yes, you can say something like that. But for the benzene molecule, it does not have cyclo, all those things. It's the next thing we're going to look at actually. So in this case, it will be called cyclohexane. Cyclohexene. Why? Because it has 6 carbon atoms and it has a double liaison at position number 1. Then it is also a cycle. That is why we are calling it cyclohexene. Now at position number 1, you have a function there that is coming out there. You have a function there. Now, this here has got how many carbon atoms? There's one there. There's another one there. There's one there. There's another one there. So like I said, you are never supposed to count this carbon atom when you're going for the substituent. You are never supposed to count this carbon atom when you're going for your substituent. So you have one carbon atom there and another carbon atom there. So it forms, that is an alkane with 2 carbon atoms. Now you remove 1 hydrogen atom. So an alkane with 2 carbon atoms is called ethane. Now when you remove 1 hydrogen atom and becomes a substituent or an alkyl, it's going to be called ethyl. It's going to be called ethyl. So ethyl will be the first substituent at position number 1, and methyl is the other substituent at position number 6. And therefore, when we are naming this hydrocarbon, that is the cyclic hydrocarbon insaturate, it will be at position number 1, you have an ethyl, and at position number 6, you have a methyl. And Lassen Principle will be cyclohexene. In the same sense, we will not give the position of the double liaison. We decide to not give it, but you can also decide to position the double liaison. If it's a position 1, you can position there. You can position it there. If it's position 2, you position it there. Is it clear? So therefore, this hydrocarbon will be called ethyl cis methyl cyclohexene. Is it clear? Est-ce que c'est clair? Est-ce que c'est clair?
Yeah.
For everyone. Is it clear for everyone?
Yes.
Guys, what's happening?
It's clear.
Okay, if it's clear, we go to. So for this part, I won't go much in detail. I'll just explain the surface because it's not part. I'm sorry, it's not part of your syllabi. So now we said we have two classes of organic compounds. We have the aliphatic and the aromatic. Now we are done with the aliphatic. Now we are going to start dealing with the aromatic. So we said aromaticity comes in as a result of resonance and mesomery. So resonance and mesomery are basically the idea that an atom will be in a state of superposition with its pi bonds or sigma bonds. Now in our case here, we are going for double liaison here, we have got pi bonds, but we also have factors that affect mesomery and all the things that happen in the benzene molecule. Now for this part, I'm not supposed to explain about the mesomery. I'm supposed to explain about the nomenclature. I'm supposed to explain about the nomenclature. The mesomery is something else. So it is because of mesomery that you have the notation with a caseco here. So the benzene molecule can be written like this with my liaisons, that is with the double liaison on on three different positions, on three different positions of the cyclohexane molecule, the cyclohexane molecule. Now, when you include three double liaisons that are alternating, like if I start here, you say one, you skip this one and you put there, you skip this one and you put there. So it is for this case that we assume that the benzene molecule can also have a stability over this molecule you are seeing here. You can draw the benzene with a caseco here because it justifies the principle of mesomery or resonance. Now we said we are here to we're here to explain about the nomenclature and not the mesomery. So benzene is the buildup for all aromatic compounds. For all aromatic compounds. So we have got naphthalene, we have aracena, we have phenarathene. So all these compounds are used to build up different aromatic compounds. You have the one that is used to make vanilla in anything, that is ice cream, all those things. It's here. You have hydrocarbons that are used for, that is the building up of amino acids. There are those ones that contain the benzene ring. For those that are doing biochemistry, that is phenylalanine, tryptophan, and triosine. These three are the three aromatic hydrocarbons that you are going to look at in biochemistry because they are the only ones that contain the benzene ring. So when you look at the benzene, when you look at a molecule and it has got a benzene ring attached to it, if it has a benzene ring attached to it, please take note that it is an aromatic compound. It is an aromatic compound. Les composants ayant un cycle benzénique dans leur structure sont dits aromatiques parce qu'un grand nombre d'entre eux sont des odeurs agréables. They are called aromatic compounds because they have got pleasant odors. They have got pleasant odors. Now we are saying they have pleasant odors because of the benzene ring. It does not mean that the benzene derivatives are esters, because you guys have also done what we call esters. Esters are derivatives from carboxylic acids and alcohols. They are different from the benzene cycle. They are different from the benzene cycle. Esters also have got the aromatic. They have the aromatic factors also. That is the agreeable smell, the taste, all those things. So when it comes to nomenclature for the benzene molecule, we are going to look at the positions at which they are attached to different hydrocarbons. That is in the case where you have a substituent. Now, if this is a benzene molecule and this is our chain principal, this is our chain principal. So if at carbon number 1, like we said, for a cycle where the substituent is, that is where our position of where the substituent is, that is where we start counting from. So our substituent is at position number 1 here. This is going to be our position number 1. Now, when you're naming this hydrocarbon or benzenic ring, it will be called methylbenzene. It will be called methylbenzene and not cyclo. Some of you might call it cyclohexene. Then you count, say, okay, at position number 1, at position number 3, at position number 5, you have got a double liaison. No, the benzene molecule is not called cyclohexene with the position of the liaisons. No, it is called the benzene molecule. It is called benzene. I know it looks like cyclohexene, cyclohexane, all those things, but when you have got alternating liaisons like this, or you have a caseco, just like that, if you have a hexene with a caseco inside, it's a benzene. Not that it's a benzene molecule. So the nomenclature would be the chain here is benzene, and there's a substituent, and the substituent is a methyl. The substituent is a methyl. So if this substituent is a methyl, the name will be methyl benzene. It will be methyl benzene, which can also be called toluene. It can also be called toluene. Then when you go on the other side, when you go to the other side, forget about phenylmethane. I'll come to this one later on because you've not learned about the arrangement of the hydrogen atom. That is for the phenyl radical. So I'll come to this later. Then we have
Because nanga kaja ka formula kaja ka 4n plus 2 kama bazabwa 4n plus 2.
4n. Ah, yes. Okay. Okay, that's a very good question. So in the case, this is now where you come to the aspect of mesomery. So in the case where you want to determine if a compound is aromatic, you're supposed to take into consideration three main factors. The first factor is you are supposed to have a cycle. Let me just get a picture of the part of the polycop that explains about the mesomery. Then I share it with you guys so that when I'm explaining, you can follow. So you are supposed to have a cycle. The second one is there is supposed to be double liaison. That is in the case. You're supposed to have at least double liaison. Then later on, you are supposed to satisfy the 2, that's the 4n plus 2 that Samuel is talking about. So the 4n plus 2 basically just shows us the entier, the number of the number of carbon atoms that this molecule has. And when it is entier, if it is definite, it means that that compound is aromatic. If it is entier, if it is a whole number, it shows that it is aromatic. But if it's not a whole number, it shows that the compound is not aromatic. So let me just get a picture and share it with you guys. Organic chemistry, majipa BCG. Okay, yeah, it's good to always study ahead. Eh? So let me just get the picture and share it. I hope it's going to be clear. Just a minute, yeah. Okay, can you see it? Can you see it?
Yes, we can.
So now the idea is for you to satisfy. Now this is now the part I was talking about, the aromaticity and the resonance. If you can see here, there's what you call hybrid resonance and all those things. So when you look at resonance and stability, this is when you understand how these benzene chains are formed and how the alternating liaisons that is in the benzene molecule come in. Now, to just answer Samuel's question, what the formula here is just to explain the delocalization of electrons, and therefore, how do you satisfy that principle? Now, this is how you use the formula. So you count how many carbon atoms you have in this molecule. Hmm?
6.
You have 6. So it's going to be 6 is equals to, if you can see from the formula, can I increase this? Okay, yeah. Can you see? Can you see?
Yes, we can.
So that we know. So it is great. Please, the formula is here. Eh? It's coming from me. I've not brought it from, this is just my polycopy. I've just got a photo and I'm sharing it with you. This is the formula to find out if, because for an organic compound to be like here, pour une molécule organique soit aromatique, elle doit être satisfait les trois conditions. Trois conditions. If it only satisfies 2 of them and does not satisfy 1, it means it is not aromatic. Est-ce que c'est clair? Is it?
Yes.
Okay, it's clear, cancer. So it is that we have 6 carbon atoms in this chain. Now, the 6 carbon atoms, that is going to be 6 is equals to 4n. We are calculating the value n here. N, entiel naturel. It's supposed to be a whole number. It's supposed to be a whole number, and it should be a natural whole number, in other words. Natural numbers start from where? From 0 or from 1? Where do they start from?
1.
Natural numbers start from 0.
Exactly. We are kamba one yambocha ntenda nalizo.
French system.
Neza kamba ya kuzamza.
Sorry. Yocha ukamba one. You should start attending analysis. So natural numbers start from 0. They start from 0. In analysis, I know in analysis you always say n étoile. I know when you say n étoile. Now in our case we do not have n étoile. Sure. Yeah. So it's n, just n, natural. So if it is entier, if it's a whole number, then it is also plain, then it is cyclic, then it satisfies the condition of aromaticity. So for this one, we have 6 carbon atoms. So it's going to be 6 is equals to 4n plus 2. And when you calculate, this is just simple mathematics. That is going to be 4, that's 6 minus 2 is what? Is that see, yeah?
4, then subject to formula n is equal to 1. Okay.
Okay, yeah. So the 1. Then it is also plain. It is plain and it is also cyclic. The benzene molecule is plain and is also cyclic. Same applies to this one. That is 1, 2, 3, 4, 5. Now 5. What's this? 5. 5. What is 5? None. What am I saying? 5 carbon atoms. Now, because we have a carbon atom that is going to have an ion here, because in your further studies, that is for those guys that will go as far as mechanism reactionnel. They're what you call carbocations. When a carbon atom forms a cation. When a carbon atom forms a cation. So we know and understand that the carbon atom being a nonmetal, it attracts electron. It attracts electron. So in our case, because we've lost an electron, we are having a more there. We are having a more. We're expecting another carbon atom to be in a liaison with this one. So in the case, in the sense of counting, or in other words, other than counting 5, we're also going to include the one that is going to come from another atom. That is an atom of carbon. We are going to include another carbon atom that is going to come from anywhere. Anyway, that's going to come whatever reaction that you're going to have, either SN1 or SN2, E2 or E1. They're what we call E1 and SN1. They also call E2 and SN2 reactions. So the explanation I'm supposed to just give here is when you count the one that is also coming from this other compound, that is a carbon compound or a carbon organic compound, we are going to have 6 carbon atoms, inclusive with this one here, then plus the 5 that this molecule already has. Then we are going to say a 6 is equals to a 4n plus 2, and therefore it's also going to give a 1. It's also going to give a 1. Then we are now going to state that the molecule is cyclic, of course, and it is plain, and therefore satisfies the 3 principles. That is to justify with the aromaticity. Now, there might be a question to say, okay, Dali, so how do you know that there's a compound here? So when I'm done with this sharing, I'll just give you a presentation of how naphthalene is formed. I'll just show you how naphthalene is formed because it's on another polycop. I think naphthalene is down here. Naphthalene, you've seen how naphthalene is formed there. Naphthalene is formed like this, like there are 2 benzene cycles that are attached. Now, in this case, we have a carbocation. It means there must be something else that is going to come in to complete the bonding for this one. There is going to be one that's going to come in to complete the bonding. Now, in our case, we just assume that we are going to take 1 carbon atom because it is going to be a liaison between this carbon atom and the other molecule on the other side. So same applies to the pyridine. We are going to have 6 hydrogen or 6 carbon atoms. 1, 2. So when we look at nomenclature on pyridine is one of those what do you call them in your biochemistry? Nucleic acid should be nucleic acid somewhere there. When you're doing nomenclature of something to do with an amino acid, when you look at amines and all those things, the amine can either stand in for a carbon atom or it can just stand in as an amine. What I mean by amine is it can just signify that there is an amine function in this molecule. So in our case, we are going to take the amine or the nitrogen that you are seeing here as a carbon. When we take it as a carbon, even the nomenclature changes. So there are 2 types of nomenclatures for the amine function. There's where we consider the nitrogen as a carbon, and there's where you consider the nitrogen as an amine over this hydrocarbon. You consider it as an amine over this hydrocarbon. In the same sense as ethers. Ethers, you've got oxygen, isn't it? You've got oxygen packet paria. Maybe you've got a chain. Just a minute. Something like that. You can either consider this oxygen as a carbon. It also has its own unique type of nomenclature. Or you can consider this oxygen as an oxide. Or you can also consider it to be an ether, the normal way we name the ethers. You can consider it to be an ether. But the ether with 3 different names. The first one, you just call it as ether, the normal ether names. You be called like, no, this is a 1, 2, 3. So if it's a 3-chained molecule, we call it a propane. There is oxygen and there is another substituent here to be called maybe methyl propane ether, like that. Then there's another one where you're supposed to consider 1, 2, 3, 4. Say 1, 2, 3, 4, 5. You consider the oxygen as a carbon. You also give it a type of naming. Even if it's the same molecule, you give it a type of naming also. Then you also have the last one where you name it as an oxide because you have oxygen here. You name it as an oxide. So the nitrogen here can either stand in for what's this? For carbon, or we can also just use it for the amine. Now, in our case, because we want to satisfy the principle of aromaticity, we are going to also consider the nitrogen as a carbon. We are just going to consider the nitrogen as a carbon in this molecule. So same principle, it's almost the same as this one here. It's almost the same as this one here. So it will be 6, which is equals to, at the end of the day, 1. Then another example where you have, is it non-entier for this one here? This one. For this one here. So that we finish up with nomenclature for benzene. we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8. So 8 is equals to 4n plus 2. Our n is equals to 3 over 2. Now, this does not justify avoir 4n plus 2 électrons dans l'ion ou bien pi délocalisé. It does not justify this. Now, why? It is because we said n should be an entier naturel. It should be a whole number. No, it should be a whole natural number. A whole natural number. That is 1, including 0. In a case where you get 0. So you say 1, 2, 3, 4, 5, 6. Anything decimal will not be considered to be natural. So this one here only satisfies 2 conditions. The first one, which is cyclic, of course. The second one is plain, but n is not equals to a whole number. N is not equals to a whole number. N is not equals to a whole number. In the same sense as this one here. Now, the explanation for this one is that because you do not have an electron delocalisé, which is a result of mesomery, it does not also justify this part here. Because when we are counting, we said we're counting the electron delocalisé. There's electron delocalisé. And I said in the mesomery, we are basically explaining or expressing these molecules in terms of how they relate with their pi or sigma electrons or bonds. C'est la même chose. A bond is a result of electron transfer, electron gain. So the mesomery explains the interaction between the electrons, that is the electrons from one molecule to another, or the electrons within the same molecule. So it is the reason why the benzene can be drawn with a circle. That circle you see the circle you can see in the molecule precedent, the one that we looked at in the other slide, You can represent it with a circle, or you can represent it with just these 2 dashes. So I said the circle just explains the principle of mesomery. The principle of mesomery is that this molecule is found in a state of superposition. Where the bonds here are sharing, is it electrons? They are sharing, is it pi bonds? They are sharing these electrons in a delocalized way, Or maybe let me just also share something that will help you visualize what I'm trying to have. Another picture will be coming up to just show you what I mean when I say the electrons are being shared. So just a minute. But is it clear for the 4n and thingy? Is it clear? Is it clear?
Yeah, yes, but it's clear.
Oh, I mean for everyone. Is it clear for everyone?
Inshallah.
Is it clear? Someone is saying inshallah. Is it clear? Can you guys see?
Yes,
Can you
you can
see?
see.
So what I mean is, if I mean for mesomer, this interaction here, that you can see here. Sorry, I went as far as explaining from a mesomer, which is not in this school. This interaction that you can see here, because there is some trajectory that the electrons or the pi bonds take. We can denote it like this. Because we had a bond here, we had another bond there, and we had another one there. But they can be moved. Now, we can also draw them in this way. Please, garder ça dans la tête. You've seen the way that this thing looks like. It can be drawn like this. Again, it's still the benzene. It can be drawn like that with 1, another one there, and with another one there. It's still the same. It's still a benzene molecule. Now, because we are saying the electrons or the pi bonds take, there's an interaction between the ones that are single and the ones that are double. Because there's an interaction, there is what we're calling mesomery, of course. What we're calling mesomery. Because of that, because there is movement of these pi bonds in this direction, they form this trajectory. They form this I don't know how I can call it. Is it a root? I can call it a root. They form this. They form this here. They form this. So we are saying they're in a state of superposition because if you've noticed the way these diagrams are drawn, there is this carbon at this position, and it has changed. It's now at this position here. It's at this position. It is at this position. Is it clear? Is it making sense? Is it making any sense?
Yes.
Is it making any sense for everyone?
Yes, yes.
Like,
Yeah.
if I was to draw these bonds on this one, I'll draw them in a blue pen. These bonds on the other, on this molecule, they'll be drawn in a blue pen. There's this one here, there's this one there, and there's also this one here. So now we're saying because there is movement, there is a mouvement, there is movement over, that is a délocalisation des électrons. Because of that, and the délocalisation des électrons, this is what we are calling la forme mésomérie or bien résonance. Because of that, we are going to have this type of let's say the benzene molecule, of course. This is what we're going to have. Now here we are just showing the two dotted lines to show that, okay, there was movement from this side, it went here, from here it went there, from there it went there, from here it went there. Of course, there will be loss and gain of electrons and other things. Then we are saying because of that also, we can just draw like a circle. Now the circle just shows that there is a complete revolution. That is in the case of the bonds, because the bonds are moving. It comes here, this one comes there, this one comes here, this one comes there, this one comes there, this one comes there. Is it clear? When I mention something to do with mesomery, this is what I mean. Is it clear for everyone? Is it clear?
I have a question.
Yes.
Please pause.
So the benzene ring, the way you're describing it, it's supposed to be supposed to be, let's say, an hexane. Let me say so. It can't like go further than that. It just has to be like have 6 carbon atoms bonded to each other, nothing more, or what? Because the ones that I've seen so far are.
You've seen something else?
No, I'm just asking. The question.
No, the benzene molecule is a hexane. Let me bring it from this direction. The benzene molecule. All right. The hexane has got 6 carbon atoms. 6 carbon atoms. Now, the benzene molecule is not hexane. Why? Because the benzene molecule, if you call it hexane, you'll be like, no, it is going to be hexane. Maybe say, like I gave an example, I said it would be hexane. If you count from here, it would be hexane 1, 3, 5. It would be 1, 3, 5, 3, diène. That's what you're going to call it. Now, that one is a cas particulier. This one here. You guys know what a cas particulier is, huh? It's a special case. The benzene molecule is a special case. Why? It is because of the delocalization of these electrons and the mesomery factors. The mesomery factors, there are a lot of factors. There's what you call the pi sigma n, the pi sigma, the pi Vambili, guys, Vambili. There are a lot of factors that affect mesomery. Now, because of those factors, it is not going to be called a cyclohexane. It will be called a benzene chain. So, in other words, when you have a cyclohexane molecule that looks like something that looks like a cyclohexane with 6 carbon atoms, but with 3 different liaisons on 3 different points. That is maybe this one there, the other one is there, the other one is there. You are not going to call it a cyclo 1, 3, 5, triene. No, it won't be called that. It will be called benzene. That is the reason why, if you've noticed with this molecule, when we started with the aliphatic and all those things, we said the aliphatic is made up of alkanes and alkenes. Alkanes and alkenes, the double and the single liaison. Then we said we are done with that part. That is the aliphatic, that is aliphatic linear, aliphatic cyclique. Now we came to the aromatic part now. The aromatic part, this is where we said we have a chain, and this chain is called benzene. The benzene chain is what is responsible for aromaticity. Now, for us to define aromaticity, we are supposed to define aromaticity in 3 factors. We said 1 is supposed to be a chain, of course, and it should be a cyclic chain. It should be plain and should satisfy the localization of electrons, which Samuel stated, which is 4n plus 2, and n should always be on tier. Should always be an on tier. Now, it was found out that the benzene chain, even though it has got a cyclohexane type of orientation, or like a drawing for cyclohexane, even though it has got that kind of thing, we are not going to call it cyclohexane because of the 3 factors. That is, 1, it is plain, it is cyclic, and it satisfies the 4n plus 2 equation, and therefore it is aromatic. It is aromatic. So it being aromatic, it will also have its own name. It will also have an independent name from the normal names that we're going to be having when you know cyclohexane, cyclopentane, cyclonine. It's also going to have its own name, because it is from that name now we're going to be like, okay, this is for compounds that are aromatic, and this is for compounds that are not aromatic. So it is the benzene chain, not the cyclohexane chain. No, it's the benzene chain that is responsible for aromaticity in different compounds. It is the benzene chain that is responsible for the vanilla taste in the ice cream. It is the benzene chain that is responsible for phenylalanine, the amino acid. It is the benzene chain that is responsible for phenylhydrazine, for the ozones. It is the benzene chain that is responsible for all those aromatic properties. It is the benzene chain that is responsible for all those properties. It is d'après les 3 critères. That is 1. The first one, that is plain, should be cyclic and should satisfy the 4n plus 2 equation, and n should always be an on tier. So when you have a cyclohexane, with only 2 bonds, with only 1 and 2, it's not benzene. It's not benzene. Please take note. When you have 1 and 2, when you only have 1 and 2, when you only have 1, you only have this one and this one. It's not benzene. It's a cyclohexane with 2 liaisons. But now, if you have got 3 that go like that, and they alternate, it's going to be called benzene. So professors might use this one, or they might use this one. C'est la même chose. They can use this one. They can also use this one here. C'est la même chose. Is it clear? Nambucha explain the Miriam. Is it clear?
Yes.
Is it clear for everyone? Please excuse me for going out of topic. I'm supposed to teach nomenclature. Is it clear for everyone? Is it clear for everyone?
Yes.
I'm saying, is it clear? Is it clear? Is it really clear? I ask a question. Is it clear?
I'm a little bit behind on how we are using the formula. Can you please repeat?
Okay. So where is this? Where is this presentation? Just a minute. Can you see? I'll just use the benzene molecule so that we finish up with. Can you see?
Yes, I can.
Okay. So what we are trying to say is, how many carbon atoms does this compound have? The benzene chain. How many carbon atoms does it have? How many carbon atoms does it have?
Got 6.
Just 6. So now the formula is this one, right? The formula is this one, 4n plus 2. Formula is 4n plus 2. Now we are saying it has got 6 carbon atoms, and therefore it will be 6 is equal to, so the 6 here is just the number of carbon atoms that this chain or this molecule, this hydrocarbon, this aromatic hydrocarbon has. So it has got 6. And what's the value of n when 6 is equal to 4n plus 2? What's the value of n when 6 is equals to 4n plus 2? Can you guys get me first? Conrad?
The value of n will be 1.
To be 1. Now, in the same sense, for this same example, we use the same principle. How many carbon atoms does this compound have? This one. How many?
8.
It has got 8. So therefore, 8 will be equals to 4n plus 2. It will be equals to 4n plus 2. Then what will be the value of n when 8 is equals to 4n plus 2?
Oh, okay, it will be a fraction, yeah. Be a fraction.
Exactly. And therefore, we are saying for us to have an aromaticity, pour une molécule organique soit aromatique, elle doit satisfier 3 conditions. 3 conditions. Every time you have conditions, it must satisfy those conditions for it to be called something. For it to be called Zambian, you're supposed to satisfy, I don't know how many conditions you're supposed to satisfy. Is it maybe you have the green registration card, you're born in Zambia and stayed there for 10 years, and your parents are both Zambians? Those are the conditions that satisfy you being Zambian. If one is not satisfied, so for everyone amongst you that does not have NRC, but has parents that are Zambian, and has stayed in Zambia for 10 years, but does not have NRC, is not a Zambian. It's the same principle. You have 3 conditions. That is, 1 should be cyclic, it should be plain, then it should be, what do you call it? It should satisfy the 4n plus 2, délocalisation des électrons. So P ou bien les électrons l'anion. So now it satisfies the 2, the first one and the second one. It is cyclic and it is plain, but does not satisfy this one here because n is not an entier naturel. This is 3/2. It's not an entier naturel. Is it clear?
So are we trying to say if it's not a whole number, if it's a fraction, then it's not an aromatic hydrocarbon?
Because the idea here is n un entier naturel. Un entier naturel. It's supposed to be a definite whole. Now, if I say whole number, I mean another class of numbers. It should be a definite natural number. A definite. What I mean by definite, it should be not a point, because in mathematics, 1/2 can also be. Is it, what do you call them? Is it rational or irrational numbers? Or those ones, the points. Is it rational or irrational? They come from a class also. They also have a class. Guys, you also did mathematics. What do you call them? My point, like 1.5, 1.67, 1.3, all those things. They are called, is it rational or irrational numbers?
Rational.
Hey, they're called rational numbers. So it means we are no longer in the class of natural numbers. Now we are in a class of rational numbers. You get my concept. You get my idea.
Yes.
You are no longer in the class of natural numbers. Now you're going in the class of rational numbers. Now rational numbers come from a class. Rational numbers are found in a class. Is it, where are they found in? Real numbers. Real numbers. Because real numbers contains almost all numbers. I think so. It's been a while mathematics. But real numbers contain almost all the types of numbers. The complex, the what do you call, the natural, the Q, which is the rational. All those, the natural numbers, the real numbers contain everything. They contain everything. So for us to still remain in the natural numbers, we are supposed to satisfy this n that is supposed to be a natural number that is whole. A natural number that is whole. It can be 0, it can be 1, can be 2, can be 3, can be 4, can be 5, can be 6. Are not any number between 1 and 2. No. No number between 1 and 2 will satisfy this condition here. Will satisfy this condition here. Is it clear?
Yes, it is.
Okay. All right. I think for today, we just wrap up this part and call it a day. So we are saying this is a benzene chain. N'est-ce pas? It's a benzene chain. It's a benzene chain. And it will not be called cyclo 1, 3, 5, triene. No. It will be called benzene. It will be called benzene. Now, we said in the nomenclature part, when you are naming, you are always going to start from where the substituent is. Please take note. The benzene chain is a unique chain. So when you're even counting, you don't say, because I said to say we are supposed to count from the double liaison, and therefore you're supposed to have the lowest index possible. The benzene chain does not respect that. It's just like a normal chain. It's just like a normal chain. In other words, what you want to visualize it when you're doing the nomenclature for the benzene, don't consider the liaisons. Just forget about them. Just look at them as if it's just one complete chain without any double or bien alternating double liaison. Just take it like it's just a whole chain like that. Because if you take it that it has got carbon at this position, there's a double liaison. Supposed to take the double liaison into consideration. You also take this one into consideration. You have the wrong numeration for this one here. So just take it that it's just a normal chain like any other chain, like these chains we've been looking at here. These ones here. Just like a normal chain, the cyclohexene, hexane or bien hexane. Normal chain, just normal. But its name is called benzene. It's called benzene. So we are saying at position number 1, we have a methyl. At position 1, we have a methyl. And it will be called methyl benzene. It will be called methyl benzene. Methyl benzene. Then the non-usual is called toluene. Non-usual is called toluene. You can call it methyl benzene, or then you can call it toluene. Now for the phenyl methane, I'll come to that later. Then the other part here, we also have another isopropyl. So isopropyl can be called 2-methyl-propyl. So we can call it isopropyl, this hydrocarbon here, although sorry, this short chain here. Can be called isopropyl. Then the chain that we have principal is benzene. It will be called isopropyl benzene. Can also be called camine. Camine is a non-usual. Then we have we have this one here also with an ethyl, with an ethyl function. That is the ethyl there. The ethyl. We have the ethyl there. So it will be ethyl benzene, ethyl benzene. Then remember last time we said substituents come in all shapes and sizes. That is for alkenes, and alkyls. Now, sometimes we have alkenes. That is for the ones that form single bonds. Now we also have times where we have alcyls that come from the double liaison. Now, in our case here, we have vinyl, which can also be called ethenyl. I hope you guys remember this. You guys remember this? ethynyl benzene. It can be called vinyl ou bien ethynyl benzene. Then the non-usual is sterline. So sterline is also used for polymerization. Yeah. Is it clear on this part? Is it clear on this part?
Yes.
Is it clear? No questions.
Oui.
Is it clear for everyone? C'est clair pour tout le monde?
Me, I didn't understand the other part which you were saying about the vinyl benzene or styrene. Yeah, that part.
There? The what?
The vinyl benzene.
Oh, vinyl. I said vinyl. Like we said last time, vinyl can be called ethynyl. Ethynyl is ethene. Now, when you remove one hydrogen atom from it, ethene, the one with double liaison. Ethynyl is ethene. Now, when you remove one hydrogen atom from it, it becomes a vinyl. Vinyl is a non-usual. You're going to have ethynyl. So you can call it ethynyl benzene ou bien vinyl benzene. Vinyl benzene ou bien ethynyl benzene. Then la non-usual c'est sterline. Sterline. Sterline is used for polymerization. For polymerization. Polymerization is polymerization. Is it clear? Est-ce que c'est clair?
Yeah.
Is it clear
Yes.
for everyone? From where we started, is it clear for everyone? Even from chapter 1, where we started, if there's a problem, please mention it so that we address it right now.
Can I just come in, like, just to add on what Kennedy was asking? I think just
Okay.
to help, like, everyone.
Okay.
Like, there where there's a benzene, you can just go down.
Oh, okay. Oh, sorry.
Where you're from.
Oui.
Yeah. So, like, when we're naming these
It's a question?
topology. No, I'm just adding on.
Oh, okay.
When we're naming this topology, so we start from on top, and we don't consider the point at which it's touching the benzene hydrocarbon. Not so.
Yes.
All right. So we start from the top, and we count the longest chain, and then we establish its name. Yeah. All right. That's all.
Oh, that's all you're done?
Yeah.
Okay. Is it clear for everyone? From where we started from the definition of what organic chemistry is, from the definition of what hybridization is, all those things. Are there any questions? From anything we've done so far, are there any questions? Even from a coup we've done 3 weeks ago, I don't know if it's 3 weeks or 2 weeks ago, we can still answer the question. Maquinesh question. Maquinesh. Okay. So I'll come to this part
I
then.
have a question.
Okay.
So, if someone were to ask, what's the difference between ramified hydrocarbons and aromatic hydrocarbons? What's the difference?
Okay. Can anyone answer that question? Can anyone answer that question? Guys, can anyone answer that question? What's the difference between a ramified hydrocarbon and an aromatic hydrocarbon? Is that your question, Mutali?
Yes, that's my question.
Can anyone answer this question? Can anyone? If there's no one, please mention. They said, okay, there's no one. So what we see we can do, what we can do. So, Mutale, a ramified hydrocarbon falls under the class of aliphatic hydrocarbons. Aliphatic hydrocarbons. Now, for aliphatic hydrocarbons, we said they can be chains that are ouverts. Where is it? Chains that can be ouverts like that. Then we have ramifié. Right? Ramifié is a branched. So that's why I stopped on this slide here. To just, where is it? This one here. When you look at this chain here, this whole thingy, it has got one continuous chain. Yeah, the continuous chain, that is this chain here, like that. Then it also has branches. It has got this one that goes like that, uko. This one that comes down like that. It has got a lot of branches. It has a lot of branches. And because of this, we are going to call it a ramifié. We are going to call it a ramifié because it is branched. It is branched and has different substituents, and it will therefore be called a hydrocarbon that is a ramifié. Then later on, we are done with a class of ramifié hydrocarbons. We are going to look at now the aliphatic cyclic hydrocarbons. Aliphatic cyclic hydrocarbons, which are the likes of cyclohexane, cyclobutane, cyclopropane. The likes of cyclohexane, cyclobutane, and cyclopropane. These are aliphatic cyclic hydrocarbons. You get it, eh? Aliphatic cyclic hydrocarbons. Now, when you come to aromatic hydrocarbons, everything changes. Now, the benzene plays an important role. So, the question was supposed to be, what is the difference between aliphatic hydrocarbons and aromatic hydrocarbons? So the difference is basically the aliphatic ones can be any chain, It can be this same cyclohexane, with maybe instead of you having instead of you having a liaison there. Just a minute. A liaison there, another liaison there. Then you have another double liaison. You have something else there. You have something else like that. It can be anything. But now, when you talk about the aromatic ones, it's strictly benzene. There is supposed to be a molecule of benzene for us to define that compound to be aromatic. We are supposed to have a benzene chain for us to say that, okay, this molecule is aromatic. Now, for ramifié, we can still have ramifié on benzene. Take, for instance, I'll give this one here as I'll change it from cyclohexane to benzene. It can be ramifié. Or let me use this. Let me go to the internet and use, I don't know if you know, you guys know DTT. Do you guys know DTT? Hi. You guys know DTT?
I don't know what D something is. No.
I'm saying no. I'm not only asking you. I'm asking everyone. Do you know what DTT is? DTT. Civic education anymore.
Maybe if you use the different term or something, maybe people know.
No, actually, DTT is the simplest. DTT, DDT, double D avec un T. DDT.
DDT.
Yeah.
That's poison.
Ati? Hey, Adi, what do you say?
Is it that one for that poison museum?
Exactly. It's a poison.
Yeah.
Is it diphenyl tetrachloroethane? something like that. So it can be ramified. The benzene molecule, the benzene molecule can also be ramified. So like I said, the question was supposed to be, what's the difference between an aliphatic and an aromatic? An aromatic. The difference is the aromatic should strictly have a benzene chain. Should strictly have a benzene chain. Then the aliphatic ones, they can have anything other than the benzene chain. It should, if it's aliphatic, there should be no benzene. If it's aromatic, it should be benzene and anything else that is going to come up. So I want to show an example of a compound that can be ramified. So we can have this one here, the methyl. We can have cyclopropyl there. We can have an ethyl there. We can have what are we going to put here? A propyl. Maybe we're also going to have an oxygen like that with a hydrogen. So now this becomes an aldehyde of the benzene, becomes an aldehyde of the benzene. Then if we include something like that, hydrogen and oxygen, it becomes a carboxylic acid, and everything here becomes a substituent. Everything here becomes a substituent. So if you've seen the way this thing looks like, it is ramified, it is branched. You find that at this position you have a methyl, here you have a cyclopropyl, here you have an aldehyde, here you have a tertiary type of orientation, that is maybe that's going to be tesiobutane. Here you also have a propyl. Then at position number 2 there you have position number 1, sorry, 1, 2, 3. At position number 1 you have another methyl. So it is branched but still aromatic. Is it clear? It's ramified but still aromatic. The whole of this thing is ramified. It's ramified but still has a benzene chain. So because it has a benzene chain, it still remains an aromatic compound. Then I asked the question, do you guys know DTT? Let me just go on the internet and look for the structure for DTT. DTT is a poison. It's a poison. It is a poison. So DTT stands for is it diphenyl tetrachloroethane, something like that. You know, dichlorotetrachloroethane. Okay. So let me just share this presentation with you guys. You can see. Can you see?
Yes.
Yeah. So this is what I mean. So this whole thing is still aromatic. It's still aromatic, but is ramified. It's ramified. It's a ramified. You have the chlorine there. The chlorine is bonded to 2 different benzene chains, and the benzene chains are bonded to another chlorine. Then maybe we look at these other compounds. Where are they? Let me just look for phenylalanine, some hydro. Phenylalanine, okay. Phenylalanine. Phenylalanine is a phenyl, okay. Here, this image shows the 3 hydrocarbons that are, sorry, amino acids that are aromatic. So in your, what do you call this mod you are doing? Your biochemistry. When you reach the part of amino acids, you are going to do what you call classification of amino acids. You're going to class them in those that are acidic, those that are basic, those that are intermediate, those are non-polar, those are polar, those are charged, etc. Now you're going to reach a part where you're going to class 3 amino acids in the family of aromatic amino acids. They are going to class these 3, just these 3. What you are seeing here are just isomers of tryptophan. So there's phenylalanine, triosine, and tryptophan. They are the only amino acids that contain the benzene chain, and they are therefore considered to be aromatic. They are therefore considered to be aromatic. So the benzene chain is the base, or maybe say la base, it's the base for aromatic compounds to be formed. For you to have an aromatic compound, you are supposed to have a benzene chain. It's like that's the rule. You are supposed to have a benzene chain. So in the same way, you have these compounds you are seeing here. I don't even know the name of these compounds. But all these compounds that you're seeing here with benzene chains, they are aromatic. They are aromatic because there is just a benzene. They are aromatic because the benzene is bonded to the chain principal, or beyond the benzene chain is the principal chain. Is it clear?
Yes, it's clear.
Okay. So if there are no questions, this is the end of today's cours. On se verra demain pour la chimie